Hello, linear algebra student. This video is for chapter 3.2, properties of determinant. So in 3.1, we noticed some properties of determinant and we kind of just see it from examples. In 3.2, we're going to write the theorems out, try to explain, prove it. The full proof will be in the book. I'll talk about it and we'll, try to use it and also tied it with uh, vectors independence, which we talked about in chapter 1. So knowing the fact that a matrix is invertible is important because the invertible inverse matrix theorem ties a lot with the rest of the material that we cover for vectors and span. And determinant, if the determinant is 0, it helps us to determine that the matrix is invertible. So it is an important topics. So first is about elementary row operation. If you do an elementary row operation to a matrix, in all these cases is n times n square matrix, then the determinant of the one that you result in after you do the elementary operation is called B. And we are relating determinant of B with determinant of A, which is B4. So what we have seen is if you multiply one row of A and then add to another row to produce a new matrix, actually you do not change the determinant. But if you interchange two rows, the determinant become opposite. If you multiply, if you scale something in the row of A to produce B, then you basically the determinants will be k times. So it's kind of like you factor something out. Okay. A row, one row. So scaling a row will change the determinant. And to summarize it, we'll say determinant of A is actually the pivot in all the elementary row operations matrix times together, and then it will be 0 if A is not invertible. So because every row operation actually corresponds to a identity matrix with some changes that we talked about in chapter 2. So for example, explain the properties using the following equation of determinant. So I say determinant, well, I think these should be all determinant. Okay, so to write a determinant of a vector, so if we write this, that is a vector. But if we use two straight line, that is determinant of the vector. So we'll say this determinant is equal to 3 times of this determinant because I divide this by 3. So the resulting determinants would be 3 times of the initial one. So this used the fact that when A is multiplied by K to produce B, B is K times of determinant of A. Okay, so scale by K, scale by 3. So this means this is 1/3. So this determinant is 1/3 of this determinant. So this determinant is 3 times of that. If I have again, this is determinant of it is equal to the negative of this determinant, because if you compare the two matrix, you can see that the two row 1 and row 2 swap, right? Row 1, row 2 swap will have opposite determinant. Okay, row swap. Row swap of row 1 and row 2. Scale by 3 for row 2. Right. And then the second one is if I have okay, so the second example is we would try to use the row echelon form, so apply elementary row operation to this matrix to find the determinant. One of the results that we know was the last section was if you have an upper triangular or lower triangular matrix, the determinant is the product of the diagonal. So row echelon form help us to do that. So let's do start off with a determinant of this. Determinant of A is equal to the straight line 3, 4, negative 4, 3, 3, negative 3, 2, negative 3, negative 5. So to do this, we'll see, well, this is not 1. We would actually factor the 3 out. That means divide this by 3, so it will be 3 times of the determinant of 3, 4, negative 4, 1, 1, negative 1, 2, negative 3, negative 5. And then it would equal to negative 3, the negative of this switching the two row 1, 1, because we want it to we want to use this as a prefix row. 3, 4, negative 4, 2, negative 3, negative 5. So it is very good to do elementary row operation for getting off 0 for these. So first is row negative 3 of row 1 plus row 2 put into row 2. Right? And then negative 2 of row 1 plus row 3 put into row 3. Do it all together. You see that negative 3, negative 3, 3, 3, 4, negative 4. So I would have row 1 stays the same. Row 2 becomes 0, 1, negative 1. Row 3 become negative 2, negative 2, 2, 2, negative 3, negative 5. So it becomes 0, negative 5, and negative 3. And then we need to do another row operation, which is 5 times of row 2 plus row 3 put in row 3. So that's very easy because 0, 5, negative 5, 0, negative 5, negative 3. So become 1, 1, negative 1 out of space. 0, 1, negative 1. 0, 0, negative 8. So, I should do a determinant. So I should carry negative, right? Negative. Okay, so it's negative 3. Now I can do the determinant of this. This is the upper triangular matrix. So 1, 1, negative 8 is the determinant. So negative 3 times negative 8, that is 24. So this determinant is equal to equal to positive 24, and that's the answer. Use elementary row operation along the way. If there is a scaling, you move it out. If there's a switch of row, you do negative. Do another example. We have this big 4x4 matrix. If we do cofactor expansion, you only can, it's almost all field. You have to do 3 by 3 cofactor. It's kind of a lot. So whereas if you do row echelon form, it's easier. So what do I need to do? I would, I have a 1 here, so it's ready to do the row. So we'll say determinant of A is equal to actually 1, 3, 2, negative 4. Just copy it. 0, 1, 2, negative 5, 2, 7, 6, negative 3, negative 3, negative 10, negative 7, 2. So this is already a 0, so I just need to get rid of the 2, 0. So negative 2 of R1 plus R3 put into R3, and also 3R1 plus R4 put into R4. So write the scrap paper here, negative 2, negative 2, negative 6, negative 4, and 8. Add to 2, 7, 6, negative 3. So I keep 1, 3, 2, negative 4 as R1, and then R2 is 0, 1, 2, negative 5. Don't change. R3 now become this together, 0, 1, R2, 5. Oh, this is almost the same. And then what about that? The R3, so it'll be 3, 9, 6, negative 12, because I times 3. And then add negative 3, negative 10, negative 7, and a 2. So you see a 0, negative 1, also a negative 1, and then a negative 10. So you can see this 2 0 is the one that we need to get rid of. So row 2 negative row 2 plus row 3, put in row 3. Negative row 2 itself plus row 4, put in row 4, right? So let's do 2 one more. 1, 3, 2, negative 4, 0, 1, 2, negative 5. Negative 1, so 0, negative 1, negative 2, 5. Add to 1, 2, 5. Right? So I have 0, 0, 0, 10. And then the other one, we'll just add this together, so I don't need to do scratch paper. So 0, 1, this add together is 1. This add together is negative 15, right? So you do this determinant. I didn't switch anything. I didn't scale anything. So these determinants are still the same. I should use the determinant form. And then I would kind of switch column now because I have 1 here, right? Well, actually, I think I can get rid of this 1. So get rid of this 1, 1, 3, 2, negative 4, 0, 1, 2, negative 5, 0, 0, 0. Get rid. Oh, how come? 0, 0. I think this is already 0, 0. So I just need to switch the 2, right? 1 and negative 15 and 0, 0, 0, 10. But because I switched the 2 column, row 3 and row 4 swap, so I do negative, and this is an upper triangular, so the determinant would be negative of 1 times 1 times 1 times 10. So it's equal to negative 10. So that is one way to find. It's a little faster. If you're good at elementary row operation, it's a little faster than cofactor expansion. And you can also see that when you are doing this, just imagine if you have anytime we have a situation where we have A, B, C, D, for example, for 4, and then this is a dependent row, 2A, 2B, 2C, 2D, you can change this into A, B, C, D using row operation 0, 0, 0, 0. And you see that this would stay at the end, no matter what you do in the middle. And the upper diagonal would always be 0, right? Or the one of the products in the diagonal is 0, so the determinant will be 0. So this tells us that if columns are independent, then A is invertible. So other than checking, well, if rows are dependent, then they are not invertible. And it has to do with the fact that because of the product things. Okay, so it must be invertible if you have one of these number being 0, then it's not invertible. And also another things that you can see that when we're doing row operation to find determinant, if you see multiples of rows that are dependent of each other, that means they are singular, they are not invertible. So seeing multiples row other than seeing multiple column, which is supported by the inverse matrix theorem, also tells us if a matrix is invertible. Okay, so in practice, we can actually increase the statements in the invertible matrix theorem, saying that if I know the determinant of a matrix, if it is not 0, then the matrix is invertible. And that would means all the columns are independent. That means the columns span Rn for a square matrix A. Okay, so this is part 1 of 3.2.